Hello, guys. So let's continue our discussion about rectifiers, diode rectifiers. So we take this circuit last time, and we discovered that this circuit, really produces some sort of DC. Okay, and we said that the ideal voltage model or the ideal diode model in which the diode forward bias voltage would be just zero. Okay, is really very good for such circuits. Okay, why? Because usually the input that we are trying to convert to DC voltage has a very high magnitude or very high maximum voltage or peak voltage. Like for example, our standard outlet. I have mine here. So each time I just point to this location. So the standard output, is 110 RMS, voltage RMS. And when you convert RMS to maximum, just the normal thing that we do, this maximum here voltage, it would be 155 or 160 volt, which is really great, very, very greater than 0.7. So we can just ignore this 0.7. Actually, in the lab, when you do that experiment or multisim, for example, you will not notice this 0.7. You will if by just your first look, you will think it's just zero. Okay, so let's apply the diode ideal model because it's important to know how to deal with these circuits in both way with the constant voltage model, like what we said, like what we discussed last time, and here is with the ideal voltage model. So the ideal voltage model again is very simple. The diode just needs 0 volt from the input to conduct. Okay, so whenever you see the diode is in forward bias, then it's on, and whenever you see the diode in reverse bias, then it's off. Okay, so let's start here by the Wasp half cycle or the first half cycle, in which the positive will be in that location and the negative will be in that location. And this is the direction of the input. Okay. And we call it positive half cycle, although assuming that the direction will not change. I mean, all the time, this terminal, let's call it A, will be positive, and this terminal, let's call it B, will be negative. Although in our analysis, we usually change it in each half cycle. Okay, so in the positive half cycle, or the first half cycle, whatever you call it, you can represent this circuit with a battery like this, although this battery has a variable voltage, but all the voltage it produces is positive voltage, like 5, 4, 1, 10, whatever. It cannot be -1 or anything minus. It always positive. So in that case, since the input is greater than 0 all the time, or positive, we can say, then the diode is forward. Okay, that is forward. Now, since it is an ideal diode, then the diode is on. Okay. So VD is equal to 0. This is our first unknown. And remember, we are concerned more here about the output, the voltage that will go to the load. Here is the load, RL or R. Because this is the load. This is, for example, your phone that needs the battery of your phone that needs DC voltage. How about VR? Let's apply Kirchhoff voltage law. So if we look here, these are the directions of the voltages. So we're gonna see that VO plus VD equal to VN, V input. So VD is 0, as we see, because it's ideal model. So VO is equal to VN. That's very simple. Okay. Last time when we dealt with this, we divided this region into 2 regions, when V input is greater than 0.7 and when V input is less than 0.7. Here we don't need all of that. Okay, number 2. Okay, the second half cycle. I will not call it negative. Okay, so the second half cycle. In the second half cycle, let's do this analysis with red, for example. We will have the negative here and the positive here. And the direction of the voltage will be in that way. But remember to flip the polarity of the signal here. So this would be our new input. Remember, this blue curve, this blue sine wave, okay, that has a positive half cycle and a negative half cycle are plotted, assuming that the voltage is all the time positive at A and negative at B. Okay. So this will give you a battery with positive voltage in the first half cycle and a battery with negative voltages in the negative half cycle. We said that you can flip the terminal, you know, but it changes the polarity, the sign of the voltage. So in both cycles, in both half cycles, you will have positive voltage, but one is negative positive, negative at B, positive at A in the first half cycle, and another one that has positive at B and the negative at A. And when you do that, then the direction of the voltage has flipped. So here we flip the direction and flip the sign of the voltage. Two things. So we're gonna call this V input dash. This one here, which is in red. And at the middle of this half cycle, in the beginning we have minus Vmax, here we have positive Vmax. So let's draw this circuit now. A battery that has a variable voltage, that's fine. Then a diode, then our load. And here is VO, here is VD, and now this is VN dash. One may say, can I work with the original polarity? I mean positive at A and negative at B? Yes, and you will have negative voltages. But now we're gonna say that, okay, the diode is reverse, because although it is still positive negative, but because the sign of the voltage is negative. Okay. Okay, that's very good. Now the diode is reverse. Based on that, the diode is reverse. So the diode is off. So in all that half cycle, ID or I, whatever you call it, equal to 0. So VR or V load or V output equal to IR equal to 0 as well. So VO here is equal to 0. Very simple. Now by Kirchhoff again, and now look at the polarity change, the flipping of the direction. So now VO plus VD plus VN dash equal to 0. VO is 0, so VD equal to minus VN dash. If you work with the original polarity, it will be just Vn. VO is equal, VD is equal to Vn. Okay, so let's now draw such outputs. Okay, so let's start by the first half cycle, which we can call the positive half cycle. Okay, so in this half cycle, VD is 0 and VO is equal to V input. So let's start by VD because this is the easier one. So VD is 0, just 0 here. So all these points will be 0 in the positive half cycle. And V O is equal to V input. So this is the input, remember? So just copy this dome here, this part of the sign, and put it at VO. So I'm gonna draw it again. And again, this is just copy and paste. And why I'm insisting in adopting sine waves, although this is applies for triangular, square wave, any kind of wave will have the same analysis or same approach, we can say, in analyzing the circuit. So because this is basically what you're gonna find practically. So the output from the standard outlet in your home is just a sine wave. Okay, so this is also Vmax here. Now let's do the negative half cycle. Let's do with green, for example. So the second half cycle or negative half cycle or whatever you call it. In here we have VO is equal to 0. So this is really easy. Just make 0 here. And VD is equal to minus Vn dash. This Vn dash, here is Vn dash, positive. So just take this dome here and flip it. Or if you work with the original polarity, positive, negative all the time, positive at A and B and negative at B all the time, then V at that time VD will be equal to Vn dash, not minus Vn, I'm sorry, Vn. So you're gonna take this negative half cycle and just copy paste it here in VD. So let's do that. Here is minus Vmax. Okay. Now let's look at the output here. Okay. Let's look at the output. So here, remember, we want to convert from AC to DC. AC is variable in value. So the value of the source or the voltage is changing with time, and vary also in the direction. So here, for example, the input in this half cycle, if this is the input here, this is A and this is B, this is positive, this is negative. But here the input is like this, AB, this is now negative, this is now positive, and the direction is changing. Or it changes in sign if you keep the same, or if you keep the same polarity. So here with the same polarity, positive at A, negative at B, we will have positive, and here with the same polarity, positive at A and negative at B, we will have negative values. Negative, so negative sign for the output voltage. But here, look at the R load or VO or V load, whatever you call it. Look at this. So it's yes, it doesn't. It's changing with time, vary with time, but we have achieved 50% of the characteristics, because the second characteristic, which is changing in polarity, is not holding time. I mean, this doesn't change in polarity. So here you have positive, negative. This is the load, for example, positive and negative. You either have a current flowing in that way, or you don't have here. So in that half cycle, you will have a current flowing from this point to this point, like this point to this point. And in the negative half cycle or the second half cycle, this current will be 0. So you have either current flowing in one direction, or no, you don't have a current. Okay. If you remove this diode, the output of the resistance would be exactly the same as the input. So you will have current flowing that way in the positive half cycle, and in the negative half cycle, it will be flowing from that in that way. So the current will be changing. Here we have one current only. Okay. And also by looking at that output, we can say that this is really half-wave rectifier, because this is the main principle for it. To rectify a signal, it just ignores part of it, half of it, and just considers the other half. So you will have one polarity or one direction or one current in the output. Okay, so that's basically the analysis of our half wave rectifier, this very simple circuit that we that we can be considered our first step in order to achieve higher conversion. I mean, now our target now is to increase, or to reach the first characteristic of DC, which is we could unify the direction, but we couldn't unify the value. We want something that is really constant all the time, some output, some voltage that doesn't change with time. So this is our target now. Okay, so to achieve that target, we should analyze or quantify our DC here. Okay, so yeah, we just analyze now by looking and try to describe this situation using English. Okay, but in the next video we're gonna analyze or quantify our achievement of this circuit and how we can determine in a quantifying way our DC output. Okay, so we're gonna mathematically do some analysis, very very short analysis, to determine the amount of DC that we take out of this circuit. Then we're gonna build upon that number. As long as this number increases, then we are going in the right way. Thank you very much for watching this video, and see you in the next video. Bye-bye.